the cloud.
All right, welcome everybody to the 8th and final session in our Agile MBSE Lunch and Learn series, presented by Incozi, featuring Dr. Bruce Powell Douglas. This session is focused on MBSE and safety analysis. I'm Andrew Muxon. I'll be the host, the Incozi host today. I'm a member of the Heartland chapter. So with that, we'll just kind of talk about the Lunch and Learn series overall. Hopefully you've participated in other series. They are recorded. We talked about modeling, use cases and requirements, ICDs, and handoffs to subsystems and other parties, and testing. And today, in this last session, we'll be focusing on safety, as you mentioned. We also have a commercial sponsor for this, Smith & Nephew. So keep that in mind, and a number of regional chapters. If you have missed any of the previous recordings or just have an interest in watching them again, they're available on Dr. Douglas's YouTube channel, as well as the Great Lakes North Central Regional website, incozi.org/GLNC. And just as some kind of updates and status, note that the Great Lakes North Central Regional Conference was postponed due to COVID. We're rescheduling for the fall of 2022, tentatively planning for October 4th through the 7th. And as kind of an offshoot of this series, we're working on an MBSE Challenge Team program, and we're kind of working through the details of that currently. So we'll just look for that. In general, about Incozi, we were founded in 1990, almost 20,000 members, 74 chapters, 35 countries. That's the organization organizing this particular presentation, supporting it. We have 3 sectors: the Americas sector, the European sector, and the Asian Oceania, with 16 and 9 chapters respectively. As I mentioned, this series is organized by the Great Lakes North Central chapter in, the region, and it's made up of a collection of chapters, as you can see on this map. So you can reference those, please, especially if you're in the area, please consider joining these chapters and getting more involved. This is a list of the corporate advisory board members. If you work for one of these corporations, please take advantage of that CAB membership. You can get access to a considerable amount of the Incozi resources just through your organization. And so we certainly appreciate that membership. And if you're looking to get more involved in Incozi generally, there are a number of working groups and initiatives. We've highlighted some here that are focused on MBSE in particular, but there are, the number is changing, but approximately 55 working groups currently operating, and you can certainly be a part of those to help work through them. As a FYI, the international workshop is announced. Registration's open January 29th through February 1st of 2022. It's both a in-person and remote options there, so please feel free to look at that. It's an opportunity for the various working groups that we just displayed to come together and collaborate. And in general, if you're not familiar with Incozi, you're interested in advancing yourself as systems engineers, visit incozi.org to learn about membership, the certification, the SEP program, joining a chapter or a working group, volunteer and leadership, publications, meetings, and information like that. As part of this series, we do have a door prize, session 7. Door prize, the book Agile Model-Based Systems Engineering Cookbook, written by Dr. Douglas, was won by Norm Eckhart of Eden, New York. So congratulations to Norm. We will be giving away another book, but you need to be present to win. So hopefully, hopefully one of you today will be the lucky winner. That'll be announced after the presentation, but prior to questions. So please stick around for that. All right, finally, I'll introduce Dr. Bruce Powell Douglas. He has a deep and broad experience of over 40 years, specializing in both model-based systems engineering and model-driven development for embedded software and safety critical systems. And I will pass it off to him to tell us about MBSE and safety analysis.
All right, thank you. Let me share my screen. Here we go. And welcome everybody to this last Lunch and Learn lecture. We've talked about a lot of different interesting topics, at least I find them interesting, on MBSE and modeling and so on. In the environments in which I work, safety criticality is one of the common aspects, whether it's working on missiles or aircraft or medical systems or submarines or nuclear power plants. Safety analysis is a big part of all of that work. And the question comes up, how do I integrate that with my model-based system engineering? The workflows are discussed in my books, and I've talked about it elsewhere. We'll go in a lightweight way through some of those workflows and some of those techniques in this discussion today. This, of course, is a huge topic, and I can't address even most of the topics. So I've wanted to focus here on specifically how do I integrate MBSE with safety analysis using SysML and Raster CAMU style modeling tools, and a quick, easy workflow so I can build up a safety analysis for relevant systems as I'm specifying those kinds of system properties that I want to do. Okay, so MBSE and safety. So the first question is, so where and when do we consider safety in MBSE? To which my answer is, well, yes. We really consider it all the way through. Some people who don't have perhaps deep experience think that, oh, well, we do safety analysis, either at the start or at the end, and then we're done. That's not how this works. Safety analysis needs to be a continuous, ongoing effort as you develop your system specifications and designs. Early on, we start off with this initial safety analysis. So what I do when I start analyzing the capability of systems using use cases and which you can trace to requirements and user stories and all that stuff we talked about earlier. In that context, I consider the safety. So I'll consider, I'm going to do manage navigation for my aircraft. Well, what are the safety impacts of the requirements and services and behavior that goes on to achieve that capability of this system, of this aircraft? So as I model my use cases or user stories, I'm worried about functionality, what has to happen, what are the verbs of the system with respect to this use case, but also the qualities of service, how much, how fast, how well, how much capability, what capacity, and so on. One of those qualities of service is safety, and we'll talk about what that means shortly. We also focus on things like logical data schema. When I talk about pass information around, what does that information consist of? What does it entail? To what degree of precision do I need to specify it? And those sorts of questions. Those are all part of my logical data schema. I specify my logical interfaces between my system and my actors, or in the context of a subsystem architecture, how the subsystems interact in terms of flows, invocation of services, synchronously and asynchronously. What are the system functions used in the context of this use case capability of the system? And then dependability, which consists of security, reliability, and safety. We'll talk a bit about that shortly. So we do this initial safety analysis, but every time we take a step in our process, we introduce the possibility of compromising our safety of our system or introducing new safety concerns. So we have to reevaluate our safety stance and see, are there additional safety means or measures that we need to take place to put in force in order to keep our system safe. So look at this is the Harmony Agile Model-Based System Engineering process. And we have a number of kind of activities here, such as defining our stakeholder needs, specifying and analyzing the requirements, doing architectural tree studies and analyses, doing some architectural design, doing some handoff to downstream engineering, and then incremental process, we would do this many times, usually some small number of use cases at a time. If you do a kind of traditional V cycle, you maybe do this once. That's okay. This discussion doesn't change really whether you do this once or many times. As you develop these use cases, we will introduce safety concerns and concepts and work in every one of these activities. So the question of where do we consider safety, the answer is kind of yes. All the time we have to consider safety. As you make functionality decisions, capability decisions, or technical decisions, we are potentially affecting safety, and we need to evaluate its impact on safety. Now, something I've seen some people do, I can't disagree with this approach more, is to have like a safety use case. I don't think that makes sense because with respect to what the system does, you have to consider safety impacts. So rather than have some sort of a safety use case, and then we've got all our functionality, we can't consider safety independent from the functionality. The reason why use cases work as an analytic means is because we can analyze them for completeness, consistency, correctness in isolation. And because safety impact has such a huge effect on functionality, we can't consider them in isolation. We have to consider the safety needs as we consider the capability requirements. So I don't believe in having a separate safety case. We do need to address safety concerns, but they're distributed throughout all of the use cases as we do our use case analysis. So what the heck do we mean by safety? Safety is freedom from accidents or losses. So normally we concern ourselves with human injury, human death, or animal death or injury, but it can be applied to any system where we have outcomes we want to avoid. I have applied this financial circumstances for some banks. We want to avoid this kind of situation. How do we analyze that and address that? So it is more generally applicable, but mostly we're talking about human injury and death. That's what we're trying to avoid. Safety is not the same as reliability, although it's a related concept. Reliability is a stochastic measure of the availability of system functionality. Can I provide services? And what is the stochastic nature of failures in that system? That's not the same as safety concerns. Some functionality may fail and have no impact on safety. There may not be a failure, but there could still be an impact on failure. So they're really independent concerns. They're related because often failures lead to safety concerns, but not necessarily. Safety is also not security. Security is freedom or prevention of theft, attack, interference, espionage on a system. It may or may not have safety concerns. Just because somebody steals your credit card number, that's not necessarily a safety concern. They might, steal your pictures from your vacation. That's not a safety concern. But it may have safety impacts because penetration of a cardiac pacemaker, to take control of the pacing, an attacker takes control, that could have definite safety impact. It could turn off pacing, for example. That would be bad, right? So again, separate concern from safety. Considered together, these three things, these three concepts form the pillar of what's called dependability, safety, security, and reliability. Resilience is a related term, as it applies more to reliability, but is the ability to provide services even under unexpected and unplanned for circumstances. And it not only includes dependability, but also the ability of a system to adapt to a changing operational environment. An accident is a loss of some kind, or a hazard is a condition that leads to an accident. So if you're driving your car and the brakes failed, that's not an accident. That's a hazard. It's a condition that leads to hitting the tree, which is the accident. So the accident or mishap is the actual loss or bad thing happening. Risk is a product of two values. One is the severity of the accident, how bad is it, and the likelihood of the accident. It's a product of those two values. With respect to hazards, I think of them as three different kinds of hazards. We have intrinsic hazards. You have an aircraft. It flies in the air. The fact that it might no longer fly is intrinsic to being an aircraft and doing a capability of air flight, right, air travel. Regardless of any technical means, you're up in the air, gravity sucks, bad things can happen. It's just intrinsic. Extrinsic hazards are hazards due to the operational environment. Lightning strikes because you're in a weather cell would be an extrinsic hazard. Technological hazards are hazards due to how you've chosen to implement some functionality. So you put in electric motors in your aircraft, and now you've got these big honking batteries. You can electrocute somebody with that. That can't happen if you just have diesel engines. There's not enough electrical power going around for that. So because we've selected this technology, that introduces itself some hazards. The reason why I like to characterize it this way is because it allows us to formalize our thinking about what can go wrong, what are the effects, and what we should do about it, or our safety mitigation and safety control measure means. At the end of the day, the outcome from safety analysis is primarily requirements that specify safety control measures. Now, safety control measures is an action mechanism to improve the safety of the system. This is done in one of two ways. Either it reduces the severity of the accident. For example, you might have a concern that your brakes fail, the brake pedal assembly fails, so you can't, and cause the car to stop, and you don't want to hit the tree. By any airbags, it doesn't make the accident less likely to happen, but it makes it less severe should it happen. Or safety control measures reduce the likelihood of the accident. Maybe you have redundant sensors, position sensors on your brake system that if one fails, another one takes over. So just because a sensor failed and can no longer detect the position of the brake pedal, you have another sensor that can take over the work. Or perhaps a divergent redundancy mechanism by which you have a watchdog which checks the health of your sensor. If it fails, it turns off the engine of the car. I mean, there are things you can do about it, but that reduces the likelihood of this hazard condition occurring. Now, it should be said that no safety critical system can be completely safe, because however unlikely, multiple failures can happen that can take down, not only provide the safety condition, safety relevant condition, but also take down your control measures that protect against that condition. So you can't make a system completely safe. You can make it arbitrarily safe. You can make it increasingly unlikely to occur at an additional cost and effort. But you can never make something completely safe if it has safety impacts. I'm doing something on the other screen there. There we go. Okay. Then we have this kind of reliability measures, FMEA and FAMICA. So failure mode and effect analysis, although sometimes you see failure means and effect analysis instead. That's a reliability analysis mechanism. And then there's FAMICA, which adds criticality. Kind of formally speaking, FMEA can only be used for reliability analysis. But FAMICA can be used for safety analysis because it adds the notion of severity, criticality. Now, having said that, it is really common that people talk about doing a FMEA, they really mean they're doing a FAMICA. So just because they say a FMEA doesn't mean it can't be used, but in the traditional definition of the terms, FMEA by itself doesn't have severity as one of the properties that are captured, but you do find it in a FAMICA. This is often used as a bottom-up approach to look at reliability of systems. So you have a bunch of components, and you look at the independent failure properties of the components to come up with a summary of how likely the services that are ultimately provided by the collection of components is to fail. So that's what a FMEA or FAMICA does. You can also use it in a top-down approach early on and use it to define the required reliability of components to achieve a necessary system of reliability. But often it's used at a kind of a more detailed design level. I tend to use it also early on in my specification approaches as well. When you specify the likelihood of a fault, remember it's a stochastic measure of reliability. We want to really focus on likelihood. And there's a few ways that people do that. One is to use just an enumeration. It's impossible, unlikely, likely, highly likely, or certain. A range, a scalar range, 0 to 10, or just a real kind of probability of occurrence, either per hour system use or per year or some measure of time. So that's also very, very common. And that's actually my preferred approach is to use actual probability of occurrence. But, different approaches are done by taken by different people. Most common representation of FMEA is in a spreadsheet of some kind or in tabular form. You can do this in models, as we will see. But a lot of people do this sort of work in Excel. So let's talk about using SysML modeling tools. I authored a UML dependability profile in 2009, integrated together a fault tree analysis profile I had done previously, and a security analysis profile I'd done previously, together to form a dependability profile. And that's been out there, I said, over a decade now, used on a variety of projects. And it supports not only fault tree analysis, and that's an example shown here is the fault tree. We'll look at fault trees a bit more later. Also FAMICA, and you can produce tabular forms for FAMICA. You can also do model-based security analysis. So while fault trees and FMEAs are pretty well established as a best practice formal techniques, same is not true for security analysis. So I defined some diagrammatic forms and a meta model and some tools for the purpose of doing security analysis, and as part of the dependability profile. It's similar in some ways to the MITRE trace tool, which basically looks at basically builds a directed graph of risk nodes and does traversal analysis to look at how things manifest in security attacks. So this does something similar to that, but it's a different underlying meta model, but it's similar. Downside is it's not the best supported. It's free and it's worth every penny. And it's available only for the Rhapsody tool. And you can get it from my website. Another tool that's out there is based on RAAML, which is the Risk Analysis and Assessment Modeling Language, which is an emerging standard from the Object Management Group. And it's available using this document number here. Here's a link to it. I like the work that they've done here. It's similar in many ways to what I had done in my profile, different in others. It's a bit more general in some respects. This, for example, not only do they support fault trees, but also support STPA, which is popularized by Nancy Levinson. I give on the last slide, I give a link to her book on that topic. Goal structure notation and explicit support for ISO 26262, which is a variant of IEC 61508, which is a standard common safety standard of several parts that's used in Europe and elsewhere. This RAAML standard, which is again still emerging, still in beta form. There are two prototype implementations. Here's a link to the Cameo implementation. This is a snapshot of the diagrammatic views and tabular views available in this profile in the Cameo tool. There's also a prototype implementation for Rhapsody available at this link. So I actually was not able to get that implementation to work on my desktop. I downloaded and ran it with Rhapsody and it just crashed Rhapsody. I don't know why. I was able to get it to work in a VM on the IBM site, but I wasn't able to get it to work. So your mileage may vary. I can't speak to how good the implementation is, but it's still a prototype implementation. It's not released yet. Well, the standard isn't released yet either. So let's talk about a simple workflow, which I call 6 steps to safety analysis. So there's these 6 steps to build a safety analysis based on fault trees. There are other approaches like GSN, STPA, but this is the one based on fault trees. One thing I want to mention, I forgot to mention before, the Cameo implementation is really based on 2 sources. One is the RAAML profile. The other one is the implemented parts of my dependability profile, not the security parts, but the safety parts of the profile. And you can tell because I did some peculiar things, if you went in specific ways, and they're replicated in the profile. So I think that's great that it's released. I'm not at all upset they didn't, give me credit, but I'm really happy that they're releasing this, because the more these techniques get used, the more they can be improved, the more impact they have on our daily lives. And that was my goal in the first place. So I think that that's great. We will actually see as we go through how the profile that Cameo provides looks a lot like the dependability profile. So with respect to the 6 steps of safety, the first thing to do is identify what are the hazards. These are these conditions that lead to an accident that you want to avoid. The upper figure here is what it looks like in the Rhapsody dependability profile. And the lower one is what it looks like in Cameo. They look the same because, again, they replicated some of the work that I did before, which is great, again. So this is hazards for a cardiac pacemaker. We see some hazards like failure to capture the heart. So capturing the heart means that when you, as a cardiac pacemaker, you send a signal out to force the heart to beat through the leads attached to the pacemaker. It forces the heart to beat. If you don't send out enough energy or send it at the wrong time, then it doesn't have what we call capture. It doesn't force the heart to beat. It doesn't have the effect that you want. So failure to have capture is a hazard. So you're trying to pace the heart, but it's just not working. Pacing too quickly. So if you wanted to pace it, 70 beats a minute, and you're pacing at 300. That would be bad. Pacing too slowly. You wanted to pace at 70 beats a minute, and you're pacing at 5. That's also be bad. Delivering too much energy, you can damage the tissue. So these are the primary hazards that you have for a cardiac pacemaker. Then we've got the metadata around, as shown here. This is actually describing the hazards where we can classify the metadata. So there's a hazard table defined in the profile that shows this metadata. The metadata is shown. There's the hazard, the description of the hazard, the probability, the severity, and the risk, which again, the product of the probabilities, followed by the safety integrity level, This is standard specific. The different standards are different safety integrity levels. So depending on what standard you're trying to comply with, you'd have different values here. And then you've got fault tolerance time and fault tolerance time units. Here's FTT and FTTU in the Cameo version. So all safety critical systems are considered hard real-time systems in the sense that there's a period of time a fault can be tolerated before it will lead to an accident, or before you can expect it to lead to an accident. So if you think about delivering oxygen to a patient in a medical situation, you normally have 5 minutes. If you're delivering 21% air kind of levels of concentration of oxygen. You have 10 minutes if you're doing 100% O2, but you have 5 minutes if you're delivering air. That's your fault tolerance time. Time would be 5 minutes. That's how long you can tolerate this fault before it would manifest as an accident, or is likely to manifest as an accident. So those are part of the metadata you want to capture, because your safety means that you're going to specify must be able to detect and respond to any failure within the fault tolerance time to maintain safety of the system. That's why it's important. Then we go on and define the hazard metadata. In the profile, these are modeled as a stereotype with tags, and tag values represent the metadata. So this is what it looks like in the Rhapsody dependability profile. This is what it looks like in the Cameo or RAAML or prototype profile. You can see that we capture the information in the tags area for the hazard element. In this case, it's collision of our system. We also want to understand the things around the faults themselves, around the hazards themselves. These include things like required conditions. So what's true while I'm doing this? What are my invariants or assumptions? So those are required conditions for the purpose of the analysis. Faults are system nonconformance. And there's a few different ways to think about what faults are, depending upon the standard you're working from. As a system developer, designer, I tend to think of faults as system noncompliance, and which can either be two subtypes, systematic or random. So systematic faults are called, what we call errors. So software only has systematic faults. It doesn't fail. Whereas a failure has a likeliness of occurrence, and is produced by a PDF, a probability density function. A random error has a failure rate. And the reason why I like this process of conceptualization is that the kinds of means you use to address these concerns, the safety control measures, differ depending upon whether it's systematic or random. And that's why I prefer to think of it that way, but it's not the only kind of conceptual mental model that people use for faults. We also have events. So there's these kind of conditions that occur. There are also events which can take place at some point in time. The driver, enables the brake. He goes into drive. He turns on the car. These are things that happen at some point in time. Some of those events can be hazardous. The wing fell off the plane at this point in time. That's a bad thing, and it's known to have safety impact. So there's just a kind of a special kind of, in some sense, in air quotes, of event that just has a safety impact, a negative safety impact in particular. Resulting condition is these other elements kind of combined together in some way to have an intermediate kind of step, resulting condition. We'll see an example of that shortly. So these are the conditions around, the things around the hazards. Then we want to describe those conditions, particularly the required conditions and the fault conditions. So we identify metadata. So if I build up a table of all the faults with all the metadata filled out, that's what a FMEA or FAMICA is. And we see they'll have things like action taken, the cause of the fault or failure, any controls in place you have to mitigate that, how do you detect it, that the fault has occurred? Is there a mechanism for detecting it, like a sensor or something that does that? What is the effect of this fault? What is the failure mode? How does this come about? Then there's description of the randomness aspect, either as NTBF or probability. They basically represent the same information, but in different ways. What do we do about it? Recommended action. And action taken is actually what we actually did about it in our design. Who's going to take care of it? Response, there's a thing called risk priority number, which is a product of several values, and so on. If you look at the safety standard ARP 4761, they do say that failure modes should include, but are not necessarily limited to, things like open circuits, closed circuits, shorts, parameter shifts out of adjustment, electric breakdown, wear, mechanical failure, et cetera, et cetera. So they have a list that you should consider, but it's not exclusive. There are other things you might want to consider as well. Those are the kinds of things you want to represent when you do your FMEA, FAMICA, and hazard analysis. So for me, the FMEA is a natural byproduct of how I do my safety analysis. So then we create the causality tree. This is a fault tree that we create. And the analysis of the fault trees is called, well, fault tree analysis, or FTA. Here is the fault tree shown in this is the, done in the Rhapsody dependability profile. We can clearly see that I drew all these icons myself, that I am not an artist. I think that's well established now. And this is what it looks like in the Cameo tool using the prototype RAAML profile. This is a causality tree using logical relations with logical operators. So like and, or, not, exclusive or, and so on, relating these conditions. So you want to look at how do these properties combine to manifest as a hazard. The idea being that we can make these less likely or less severe by adding control measures. And we add those into our resultant FTAs to deal with that hazard, to come up with an elaborated set of safety control means. So this is what it looks like in Cameo. We've got our hazard, which are any condition. And these are or operators. Or and are by far the most common, but you also see the other operators like not and XOR and XAND and so on. But you do see the other operators. But and or are by far the most common. So how do we get to pacing too slowly in our cardiac pacemaker? Well, here's an or operator. Either we've got resulting conditions, we have a time-based fault, or we have a shutdown fault, like a software shutdown or a CPU fault, electrical fault in the electronics. Or we have an invalid pacing rate. How could we have an invalid pacing rate? Well, it could be that we commanded a bad rate. We commanded 5 beats per minute. And that was a bad idea. We shouldn't have done that. Or we could have the pacemaker operating, but we go to an EMI field and it modifies the value. I've actually seen that happen, not with pacemakers, but with other medical devices, where EMI in the operating room actually changes values in the device. So it can be corrupted in place. Or during communication, there's a device called a pacemaker programmer. You set the parameters you want the pacemaker to operate at, and you download it. That's called a pacemaker programmer. I used to design those. And during the transmission, it gets corrupted. So any of those, because this is an OR operator, could lead to an invalid pacing rate, which could lead to pacing too slowly. So this is our initial kind of intrinsic means by which we could say there's these potentials for pacing too slowly. Once we have that, then we say, well, let's add some safety measures. And we'll do that by identifying things that either make the fault less likely or less severe. And we add those into our FTA, so we can then reason about the resulting effect on the safety of our system. So the primary outcome is we'll identify, we have control measures, and then we will, as a result of the control measures, because this is analysis, we'll identify requirements that require a control measure to be in place. Now, we don't usually specify the means by which the control measure is implemented, but we do need to specify the logical properties of the control measure. We want to prevent this thing. We have a control measure to sense oxygen flow. How you do it, it's up to you. But we have to sense that there's an adequate oxygen flow going into the expiratory limb of the breathing circuit for my anesthesia system. So this is the same FTA, but now it's elaborated to include our control measures. So let's get a time-based fault. How can we get a time-based fault? Well, if you're driven from a crystal, which is what CPUs do, there are ways crystals fail. They typically go in multiples, like half as fast, a third as fast, a tenth as fast. They go in multiples of the actual pacing rate. That would be bad. So you say, I wanted to do 50 and now it's going to run in 5, that would be bad. So what's the safety means we could add? Well, we could add a watchdog, which provides basic pacing at some low-level rate, so maybe 50 beats a minute. If this isn't pacing fast enough, this will step in and it'll force a basic pacing rate at a certain rate, even if the crystal fails. Now, this makes the time-based fault less likely, because to get to here, we've got an AND operator. The crystal has to fail, and my control measure must fail. Both must fail. And of course, you have this whole notion of single source failures independence. So if this fails, this cannot affect the watchdog. Watchdog fails, it can't affect the crystal, right? Independence of failure modes. But given that you've done the design well, these are independent. So the probability outcome is the product of these two likelihoods. We'll talk about computing probability later on in this talk. Similarly, if we want to have a bad commanded rate, well, maybe we have a range check. I'm expecting a value between 50 and 90 for pacing rate. And if I get a value of 5, I say, you can't do that. Or I get a value 150, I say, no, sorry, you can't do that. That's out of range. For message corrupted during communication, maybe we have a CRC, a 32-bit CRC. And we check the CRC before we accept the value. And if CRC computation doesn't match the values of the message, then it was corrupted during transmission. So we have means. Now, the only way that we could use that invalid rate would be, well, if you've got the original corruption and our control measure fails. So that's why this is an AND. So we call this, I call this at least, ANDing redundancy. So we had control measures so that for the resulting condition to manifest, you must have both the original fault and the safety control measure must fail. That makes it less likely. So let's do a quick example. So here we'll start off with, we've got the two models. This is the Rhapsody model over here, and this is the Cameo RAAML version over here. So we start with the hypoventilation. This is for a medical ventilator, used to be in operation, so it's in an operating room kind of environment. And we see that there's a fault tolerance time units, a probability of failure, there's a severity, which isn't shown here, and then there's the risk, which is a product of the severity, and a safety integrity level as defined by the relevant standard. Same information is represented in the specification dialog in Cameo for this particular model element. Then we'll construct our FTA. So we'll start off with, so what are my kind of assumptions and invariants? Well, the physicians in attendance. This is an important one in this case because we consider the physician in attendance to be part of the safety loop. If something goes wrong, our safety measure may say, notify the physician in attendance so they can take some corrective behavior. If they're not there, I can't rely on them. I can't use certain kinds of safety measures like alarming as my safety control measure because there's no one there to act on. Patient is intubated. So intubation means we take it's called a tracheal tube, insert it in the trachea so we can pump air in and out of the lungs. system is operational, so it's up and running and it's configured and for the particular patient, the patient weight and sex and characteristics. And we've passed our power on self-tests. So all of these are true for our starting conditions. And then we have the faults we're going to consider that could manifest in hypoventilation, or ventilation, which is, the patient isn't getting enough gas flow. Breathing circuit failure, so maybe you get a leak. Sorry, do that. You get a leak in the tube, where you got some intern standing on the airflow tube. I've seen that happen. Esophageal intubation used to be a big problem, where you'd actually intubate the esophagus rather than the trachea. This was pretty much eliminated by requirements that for CO2 sensors on the expiratory limb of the breathing circuit. Since the only thing in the system producing CO2 is the patient, if you don't have enough CO2, it means you're not intubating the stomach, or at least not having it flow through the lungs. Except in England. In England, you can actually insert CO2 to help people up faster, but that's England. Then you have gas supply fault, so you can run out of gas, or a valve problem. A ventilator fault, maybe there's typically a bellows, which use the shape of the breath being delivered through the breathing circuit. Maybe the bellows fails, something like that. You can have insufficient pressure to inflate the lungs. You could have insufficient oxygen concentration. So if you deliver, a great flow, but it's all nitrogen, that would be bad, right? So these are potential faults. And then we can add in our causality flows, our logical operators, and resulting conditions to elaborate this. So our resulting starting condition, normal operational start, is the and of all of these conditions. One could imagine I might have different sets of starting conditions, even for the same hazard, and I might have a different analysis for that set of conditions. So we've got our standard operating context, and one of these faults has occurred. So I put in my OR operators here. Okay. Then I start adding my control measures. So here, let's take a look at a couple of these. Breathing circuit failure. We'll have a pressure sensor on the system. And so if I have inadequate pressure in the system, that should detect the breathing circuit leak or failure of some kind, blockage. Kink in the line, or the intern standing on the tube. For esophageal intubation, I have a CO2 sensor following the expiratory limb. Now, for this to become a problem, not only must have the original fault, but the sensor must also fail. That's why this is an and here. For gas flow, I've got a gas flow sensor. For ventilator fault, I'm running continuous, built-in tests that make sure that everything's working properly. And those can detect a fault before the hazard would manifest. For the pressure, for the insufficient pressure, I've got a sensor. For insufficient O2 concentration, I've got an inspiratory limb O2 sensor to make sure I'm delivering at least 21%, or in Canada, 19% for some reason. So I've got these faults here. In addition, I've got an alarm system, because remember, my position was part of my control loop. So I want to, in various conditions, alert the physician, some intern is standing on the oxygen flow valve tube, or we have a bellows fault, so I want to enunciate an alarm in that condition. And if that fails, then that could also lead to an unnoticed fault. So even if we detect it, if the alarming system fails, the physician might not notice that there's something wrong taking effect. So this is the kind of analysis you would do to come up with your fault tree analysis. These control measures here, indicated by the smaller basic faults, would then trace to requirements. The system shall include a pressure sensor with certain properties, a certain location in terms of the breathing circuit, for certain effects. So there's a requirement for that. There'd be an O2 sensor on the inspiratory limb with certain sensitivity and ranges and so on for these effects. Right? So there's requirements that come out of this analysis, which we call typically safety requirements. And that's what's shown here. These are trace to requirement relations along here. So a couple other quick topics. What is the notion of a cut set? So a cut set is a collection of faults when taken together can lead to a hazard. Cut set analysis pares down the complete set of cuts to a minimal set that could lead to hazards. Because there's really a huge set of potential cuts that could lead to hazards. We only want to consider the ones that are sufficiently likely or sufficiently severe. That is, they have sufficient risk to be considered. So we have many cut sets. If you think about binary conditions, the inputs here are true or false, and not worry about continuous probabilities. It's true or false. If you have n conditions, there are 2 to the n cut sets. So in this example here, where we've got these 5 flows from basic faults, there are 32 different potential cut sets we have to consider. But we can trim this down. So we can trim away the ones that are either unlikely enough or not severe enough. So if you consider the entire set of cut sets, of which there are 32, really only these 3 are really of concern, where we've got A is true, B is true, and E is true. And this is don't care. Or E is true and C and D are true. Or they're all true. These are the 3 cut sets where you have to consider. All the other cut sets can't happen or is insufficiently likely to happen. That's what we call cut set analysis. So let's talk about calculating probabilities here. If you assume 2 conditions, A and B, are independent, and that's a crucial aspect, that's the independence of failure modes, and not mutually exclusive, then for A and B, the likelihood of the outcome of A and B is the probability of A and B here is the probability of A times the probability of B. Okay, it's the product of the probabilities. For an OR, it's the sum of the probabilities minus the product. The reason why we have a minus the product is we want to prevent double counting. You want to count from the B side and the A side the same condition. You want to count it once. So this eliminates double counting. So if we take our little example here, we've got the probabilities. The probability of A is 0.2, probability of B is 0.3. The probability of these 2 together, because this is an OR operator, is 0.2 plus 0.3 minus 0.06, 0.44. And the overall probability then, this is an AND, it's a product of this times the product of C, so it's 0.176. That's how you want to do propagation of probability through this causal chain on the fault tree. Now, I've used big numbers here just for illustrative purposes. Normally, safety critical systems, these probabilities are 10 to the minus 4 down to 10 to the minus 9. Okay? Depending upon the criticality of the systems under concern. These are often called out by standard, by the way. You must meet a certain level of probability completeness to be able to be certified for use in some application environment. And some other stuff from the RAAML. This is comes from the document showing the FMEA from Senator RAAML. Before, again, tabular form is pretty common. We got the items failure mode, effect, a local effect, and final effect, the cause, severity, and because it's a FAMICA, and so on. This is what it looks like from the document. A little bit different than it looks in the Cameo implementation, but that's fine. Still pretty much works the same. You got AND operators and OR operators and so on. Leads to And what they call the top event, that's really what the hazard is in the dependability profile. And there are also examples of other techniques, again, lack of time, for SDPA and GSN. Want to know more? There's, oh God, there's a lot of information out there. I do have a video on YouTube. It's called 6 Steps to Safety. There's Nancy's book, Engineering Safety World. She's talking about SDPA. There's the RAAML standard, and here's a link to the RAAML standard. I talk about some in my book, the workflows for doing these sorts of things in the cookbook. And this book I found pretty good. It's pretty much around the standard 61508. Remember, the ISO 26262 is a variant of 61508. And this is actually a pretty good book here, I'd recommend. So with that, I'd like to open the floor for questions you might have.
All right. Thank you, Dr. Douglas. Before we dive into questions, I just wanted to announce that Ed Bowen of Seymour, Indiana, is the winner of our door prize. He'll get a copy, an autographed copy of Agile Model-Based Systems Engineering Cookbook. So congratulations, Ed.
Thank you very much.
All right. So kind of going through some of the questions here in the chat, Bruce. This one from Qifeng Wang. Do you have any REX on the safety analysis done at the logical functional level of functional FMEA FTA based on functional architecture? How can we better explain the benefit of this activity?
Okay, so it's kind of process specific, because not everybody does the functional versus physical architectures. But not everybody does. Some people even have conceptual architectures as well. So different people at different levels of abstraction that they approach this. So in the logical architecture, you want to identify what are the safety concerns. Suppose we're doing cardiac pacemaker, example we used before. And we're doing logical architecture. We've got specifying pacing characteristics and different pacing modes, of which there are several different kinds, dual modes and single modes, and all kinds of stuff there. And what are the safety impacts of different kind of cardiac events, as well as external events that can impact that. And doing that in logical architecture provides a tremendous value, because you can specify what sorts of mechanisms and means you have to have in place, even if you're not specifying the actual physical implementation until you get to the physical architectural definition. So these are the things your physical architecture must pay attention to and comply with to be compliant with the logical architecture. So you don't have to worry about the advantage of logical architectures in general is that we abstract away what I call bits on a wire, the peculiarities of the particular implementation, so we can consider more global concerns. Otherwise, we tend to get buried in technical detail. That's the advantage of logical architectures. And the same thing is true of safety analysis. The fact that you have electrocution as a risk with your cardiac pacemaker, if you deliver too much energy, is true regardless of the CPU you use, or you use an analog circuit. The fact is the cardiac pacemaker means you're delivering electrical energy to a heart. That's intrinsic in the system. So specifically around intrinsic concerns, it's all, to my mind, that's all logical, right? Once you get to technological concerns, that tends to get more into the physical architecture, because we're using this kind of a battery, this kind of CPU, it has these kinds of failure rates, these kinds of failure modes, that has impacts on safety which are specific to that particular technology. But you still need to address the fact that electrocution is still a concern independent of the particular technology used. So I think that doing it logically makes perfect sense, but you still need to maintain the fidelity of the analysis and improve the fidelity analysis once you get into the physical architectural definition. So I hope that answers your question.
Okay, thank you, Bruce. And Elaine asked, when a system spec is 10,000 requirements, where do you begin, especially with cut analysis? How many faults are we talking about with a range? If you're kind of feeling overwhelmed, perhaps.
It's, to my mind, 10,000 requirements is not a particularly large system. That's what I call medium size. When it gets to hundreds of thousands of requirements, that is a large system. But your point of scalability is well taken. How do we scale up? Well, how do we scale up with requirements, dealing with requirements in general? Not just safety analysis, but just how to deal with all the functionality. You've got 10,000 requirements, 20,000 requirements, 100,000 requirements. The Boeing 727 has 200,000 requirements. How do you deal with that? Well, we divide and conquer. So what I do for MBSE is I primarily use cases or capability analysis to cluster groups of requirements together into these smaller clusters. So to my mind, and we talked about this in previous lunch and learns, a use case normally is anywhere from, a dozen to 100 requirements, that kind of level. So if I've got 10,000 requirements, I'll create a taxonomy of use cases, maybe 2 or 3 levels deep, allocate requirements to those use cases, and then I consider those against safety analysis in each one of the use cases, because I can analyze those capabilities independently. That's the point of a use case analysis. So I can take some sort of functionality and quality of service concerns in isolation and analyze them in isolation. And so that's what I do, is I have tied into my use case analysis. Part of that, you look at the workflows, part of that is considering safety impact for the capability described by this use case. So I think it's a really important question.
Okay, thank you, Dr. Douglas. Another question that came in is, as we kind of went through these slides, it wasn't the most clear how something like RAAML or the profile that you define, Dr. Douglas, really connects with the more, I guess, traditional systems engineering, like SysML language elements like blocks, behaviors, parts.
Okay.
It seems that perhaps maybe like a little disjoint. Is that maybe a misunderstanding, or is that something that's still being worked, perhaps?
No, it's still, I think it's fairly straightforward to do so, but it wasn't strongly elaborated in this brief talk, right?
Mm-hmm.
Well, right now, if you want to talk about, I've got architecture, I've got all those requirement stuff. How do I tie those together? Well, to my mind, those are really different models that may be in the same, Cameo or Rhapsody project. They're really different models because they have a specification model about what does it need to do, and you've got a design model. How do I do that, right? How do I connect those things? Same thing true with my analysis models. As part of my specification, I want to analyze what are the safety impacts. So one of the primary, and I mentioned this, one of the primary outcomes of safety analysis is requirements, right? So as I do my use case analysis, and I have these hazards, I'll do my hazard analysis for this capability under concern with my use case. I identify a dozen, 2 dozen, 3 dozen, whatever safety requirements. Those get mixed in the mix with my use case analysis then, because they're new requirements discovered through my safety analysis. Similarly, as I add in technologies, and these will be modeled typically as blocks, and these blocks have behaviors specified in state machines and activities and so on. Specify those things, those have properties like failure rates and various kinds of impacts. Those get incorporated in the safety analysis. So you have basically relationships into this other model, which can be part of the same Cameo project or Rhapsody project, but it's a way of analyzing that, right? Just like parametrics are used to analyze, properties like energy expenditure of a system, right? And what do? You do a roll-up analysis where you build up a parametric model of all the power requirements of all the different parts and add them all up into a summary, and you can do that with parametric analysis. Same sort of thing. But to my mind, that's a separate model, which relates to the architectural model of my system. So it relates in exactly the same way as these other models do. Does that answer your question?
I think so. Yeah, thank you. Dr. Douglas. Last question. We had one from Fadal, in what order would you suggest going through your 2 books, Agile System Engineering and Agile Model-Based System Engineering Cookbook?
So I guess there's 2 questions. One is going through the books themselves and going to which book goes first. I would say that the Agile System Engineering book is a bit more, I hate to use the term theoretical, but a bit more discussion, fireside chat about how do we do these things with some discussion of workflows and work products and so on. The cookbook is what it says. It's a recipe. And so it says, okay, if I have this task I want to perform in terms of work task, how do I do? What are the steps involved, and how do I specifically use the tools to get that task done? So I would say the Agile System Engineering book is more general guidance, and the cookbook is more specific, detailed guidance on how do I exactly do that step by step. Does that answer the question?
I think so. Cool. See, I think that's all the questions that we have. I know we're a bit over time, so I certainly appreciate your time, Dr. Douglas, as do many people on the chat. So thank you for presenting, and thank you to everyone for joining us and making this presentation successful. I appreciate it.
I'd like to add that I've enjoyed giving these set of 8 talks, and I hope that the attendees, that guys have found value to explore on your own and enhance your ability to engineer systems. I hope it's been beneficial.
Well, it's certainly been beneficial for me. I can't speak for everyone, but I think everyone certainly appreciates it based on the attendance and reception we've had. So cool. Okay, well, thanks everyone. We'll let you carry on with your day and have fun modeling.
Thank you, Andrew. Thank you, Bruce.